You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Model compression refers to a family of techniques designed to make large-scale machine learning models smaller, faster, and more affordable to deploy, without losing too much of their original capability. As models grow larger, containing billions or even trillions of parameters, the challenges of using them become clear. They require enormous storage capacity, expensive hardware, and significant energy to run. Compression addresses these concerns by strategically reducing the computational footprint, while retaining most of the model's predictive power. To understand this intuitively, think of a bulky textbook full of dense material. A skilled teacher can condense that content into a slim study guide that highlights the essential knowledge without overwhelming detail. In the same way, compression techniques aim to condense a large model into a more efficient form that remains highly useful. By focusing on efficiency, compression bridges the gap between research prototypes and practical, deployable systems. The need for compression arises from the sheer cost of working with frontier-scale models. Training these systems can cost millions of dollars in compute resources, while running them continuously requires powerful clusters of GPUs or TPUs, making them inaccessible to many organizations. Storing multiple versions of large models is also wasteful, especially when each task requires some customization. For deployment on consumer devices, the situation is even more restrictive. Smartphones, IoT sensors, and embedded systems cannot realistically host massive models without special adaptations. Compression is therefore essential for making advanced AI available in everyday settings. Just as industrial design emphasizes portability, efficiency, and usability, model compression makes cutting-edge AI flexible enough to leave the lab and enter real-world environments where resources are limited and costs matter. Quantization is one of the most widely used compression strategies, and it involves reducing the numerical precision of a model's weights and activations. Instead of storing each number in high-precision floating-point format, quantization approximates them using fewer bits. For example, a 32-bit floating-point weight might be approximated with 16, 8, or even 4 bits. While this reduces detail, it significantly lowers the memory footprint of the model and accelerates computation on compatible hardware. Imagine replacing a high-resolution photo with a slightly compressed version that still conveys the main details but uses much less storage space. Quantization operates on a similar principle, finding a balance between precision and efficiency. Because modern models are robust to small amounts of numerical noise, they can usually tolerate these reductions without major losses in accuracy, making quantization a practical and effective strategy. The most common precision levels in quantization are 16-bit, 8-bit, and 4-bit formats, each offering a different trade-off between efficiency and performance. 16-bit formats often provide a safe middle ground, reducing storage requirements without significantly harming accuracy. 8-bit precision is widely adopted, supported by most modern hardware, and offers substantial efficiency gains while keeping performance losses minimal. 4-bit precision pushes efficiency even further, slashing memory use and enabling deployment on very constrained devices, but at the risk of more noticeable accuracy degradation. Choosing the right precision level depends on the application. Tasks requiring absolute precision, such as medical diagnostics, may demand higher fidelity, while consumer-facing tasks, like recommendation systems, can tolerate the slight fuzziness introduced by lower bit quantization. These trade-offs illustrate that compression is never free. Efficiency gains must always be balanced against acceptable accuracy. The benefits of quantization extend beyond reduced storage and memory usage. Quantized models often run faster, since smaller numbers can be processed more quickly on modern processors, especially those designed with specialized, low-precision arithmetic. This speed-up directly improves user experience, reducing latency in interactive systems such as chatbots or virtual assistants. Quantization also lowers energy consumption, which is particularly important for mobile and embedded devices where battery life is a concern. By making models lighter and faster, quantization enables AI to spread into environments where high-resource infrastructure is not available. In practice, this means a voice assistant on a smartphone or a smart sensor in a factory can leverage advanced AI without needing a cloud connection for every computation. Quantization thus empowers real-time, local processing that is responsive and sustainable. However, quantization also comes with trade-offs. Reducing numerical precision introduces approximations that can degrade accuracy, particularly for tasks requiring fine-grained sensitivity. For example, lowering precision too far may cause a model to misinterpret subtle patterns in financial data or overlook rare but critical signals in medical applications. Moreover, not all hardware supports ultra-low precision equally well, meaning specialized libraries or accelerators may be required to realize the full benefits. The key to successful quantization is careful calibration, identifying which parts of the model can tolerate reduced precision and which require higher fidelity. In many cases, mixed precision strategies are used, where most weights are quantized but critical layers remain in higher precision. This balance ensures that efficiency gains are achieved without undermining the model's overall reliability. Pruning is another central compression method, and it works by removing weights or neurons that contribute little to the model's performance. The idea is that many parameters in large models are redundant, and by eliminating them, the system becomes smaller and faster without sacrificing much capability. Pruning can be likened to trimming a tree. By cutting away dead or unnecessary branches, you not only reduce weight, but also allow the tree to channel energy more effectively into the healthy branches. In AI, pruning simplifies the model by identifying which parameters are non-essential, shrinking its size and reducing computation. The art lies in identifying the right balance between aggressive pruning and preserving accuracy, since removing too much can weaken the model's capacity to generalize. There are two main approaches to pruning: unstructured and structured. Unstructured pruning removes individual weights based on criteria like low magnitude, creating sparsity within weight matrices. While effective, this type of pruning often requires specialized hardware to exploit fully, since most processors are not optimized for sparse operations. Structured pruning, on the other hand, removes entire channels, filters, or layers, producing models that are smaller and faster while maintaining compatibility with standard hardware. Structured pruning can be more practical for deployment, but it is also more disruptive, since removing large structural components risks degrading performance. Choosing between unstructured and structured pruning depends on the deployment context, hardware availability, and tolerance for accuracy loss. Both approaches highlight the principle that not every part of a large model is equally important, and much of its size can be reduced without significant harm. The benefits of pruning are straightforward but powerful. By reducing the number of parameters, pruning cuts down on memory usage and computational requirements, enabling faster inference and lower latency. This makes models more efficient to deploy in both cloud and edge environments. In some cases, pruning can also improve interpretability, since a smaller, leaner model may be easier to analyze. Pruned models are particularly valuable in mobile and embedded settings where hardware resources are limited. They also simplify distribution, since smaller models are easier to transfer and update. The combination of speed, efficiency, and simplicity makes pruning a cornerstone of practical compression strategies, even if it requires careful design to maintain performance. Despite these benefits, pruning carries limitations. If applied too aggressively, it can significantly harm accuracy and stability, making the model brittle or unreliable. Pruned models may also underperform on tasks involving edge cases, since the removed parameters might have played subtle roles in representing rare patterns. Furthermore, the process of determining which parameters to prune and how much pruning to apply can be complex, requiring multiple iterations of training and evaluation. Unstructured pruning may demand specialized deployment environments to realize real-world gains, while structured pruning may reduce accuracy more noticeably. These trade-offs demonstrate that pruning, like quantization, is most effective when applied thoughtfully, with attention to the balance between efficiency and task performance. Knowledge distillation is a third major compression strategy, and it works by transferring knowledge from a large, powerful model, the teacher, to a smaller, more efficient model, the student. The teacher is first trained on large datasets, developing strong performance across tasks. The student is then trained not only on the raw data but also on the outputs of the teacher, learning to approximate its predictions. This process allows the smaller model to capture much of the teacher's capability while operating with far fewer parameters. Distillation is akin to an expert summarizing years of experience for an apprentice, who then learns to perform tasks effectively without needing the same depth of resources. The result is a compact model that retains much of the performance of the original while being more suitable for deployment in constrained environments. The benefits of distillation are clear. It produces models that are smaller and faster while still offering strong performance, often close to that of the original teacher. Distilled models are easier to deploy on resource-constrained devices and can be updated more quickly as data changes. They also open the door for specialized applications, since student models can be designed to focus on particular tasks or domains while still drawing on the teacher's general knowledge. Distillation enables the reuse of large models in contexts where direct deployment would be impractical, making it a versatile and widely adopted compression technique. Its ability to create compact yet capable models explains its popularity across both academic research and industry deployments. There are several variants of knowledge distillation, each focusing on different aspects of the teacher-student transfer. Logic matching involves training the student to match the teacher's probability distributions over outputs, capturing not just the final prediction but the confidence levels associated with each option. Feature transfer goes deeper, training the student to replicate intermediate representations from the teacher's hidden layers, giving it richer internal structures. Task-specific distillation adapts the process to particular applications, ensuring that the student inherits the teacher's performance in targeted areas such as translation, summarization, or classification. These variants highlight the flexibility of distillation as a strategy, showing that it can be tailored to different needs and goals. The method is not monolithic but adaptable, making it a powerful complement to quantization and pruning. Compression has become industrially important because it enables deployment of AI on devices and platforms that cannot support massive uncompressed models. Smartphones, wearable devices, IoT sensors, and embedded systems all benefit from compressed models that fit within their limited hardware constraints. In industrial settings, compressed models reduce costs by lowering server requirements and energy consumption. They also improve user experience by shortening response times and enabling real-time interactions without reliance on constant cloud connectivity. Compression thus represents not only a technical necessity, but a commercial imperative, making AI both practical and scalable across industries. Without compression, many of the most exciting applications of AI, from mobile assistants to embedded vision systems, would remain impractical. As the field evolves, compression also connects with architectural innovations such as sparse models and mixture of experts designs. These approaches distribute computation more selectively, reducing the need to activate every parameter for every input. In some ways, they represent compression at the architectural level rather than as a post-processing step. This convergence highlights that efficiency is a core concern, shaping both how models are designed and how they are adapted after training. Compression methods like quantization, pruning, and distillation are therefore part of a larger story of making AI more efficient, responsive, and deployable at scale. They demonstrate that progress in AI is not only about making models bigger, but also about making them smarter in how they use their resources. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Evaluating the success of compression requires more than simply measuring how much smaller or faster a model becomes. True effectiveness is judged by whether the compressed model retains a high percentage of its original performance while achieving substantial efficiency gains. A model that is shrunk to a fraction of its size but loses accuracy to the point of unreliability is not genuinely successful. Similarly, A model that runs faster but produces erratic results undermines user trust. The ideal outcome is a balance. A model that is leaner and cheaper to run, yet remains nearly as capable as its larger counterpart. This balance is context-dependent. In some cases, a 2% drop in accuracy may be acceptable if it allows deployment on mobile devices, while in high-stakes domains such as medical decision support, even small degradations may be intolerable. Careful evaluation ensures that compression delivers real value rather than hollow savings. Benchmarking compressed models is therefore essential. Researchers and engineers use standardized datasets and evaluation tasks to compare compressed systems against their uncompressed baselines. For example, a compressed translation model might be tested on widely recognized benchmarks like WMT datasets, while a compressed summarization model might be evaluated on CNN/Daily Mail. These benchmarks measure not only accuracy but also consistency, robustness, and sometimes fairness across different inputs. Benchmarking also reveals the trade-offs introduced by different compression methods. Quantized models may retain accuracy but produce subtle shifts in calibration, while pruned models might underperform on edge cases. In practice, benchmarks serve as the proving grounds where claims of efficiency are tested against reality. Without them, compression could easily become a numbers game focused on parameter counts rather than meaningful performance. One of the most immediate benefits of compression is latency improvement. Latency refers to the time it takes for a model to generate an output once a request is made, and it directly affects user experience. Large uncompressed models may take seconds to respond, which feels sluggish in interactive applications like chatbots or virtual assistants. Compression reduces this delay by shrinking the computations required per input, making outputs arrive more quickly. For end users, this difference is tangible. Conversations feel smoother, search results appear instantly, and embedded devices respond in real time. Latency improvements also matter in enterprise settings, where thousands of queries may be processed simultaneously. Reducing response time per query multiplies into enormous efficiency gains at scale, lowering costs and improving service reliability. In this sense, compression is not just a technical upgrade but a user-facing improvement, making AI feel responsive and seamless. Energy efficiency is another critical outcome of compression, with both practical and environmental implications. Large models consume significant power to run, and when deployed at scale, their energy use becomes a major factor in operational costs. Compressed models require fewer computations and less memory, reducing power draw per inference. On battery-powered devices like smartphones, this translates directly into longer battery life. On a global scale, energy-efficient models reduce the carbon footprint of AI deployments, contributing to sustainability goals. The environmental impact of AI has become a growing concern, and compression offers a concrete way to mitigate it. Energy savings also align with financial savings, making efficiency doubly valuable. In practice, organizations increasingly view compression not just as a performance optimization, but as a sustainability measure, ensuring that innovation in AI does not come at the expense of environmental responsibility. Deployment flexibility is greatly enhanced by compression. Smaller models can be deployed in a wider variety of environments, from high-performance cloud servers to lightweight edge devices. A compressed speech recognition model might run on a car's onboard system without needing constant connectivity, while a compressed vision model could power a security camera locally without relying on external processing. This flexibility reduces reliance on centralized infrastructure and allows for distributed intelligence across devices. It also improves privacy and security, since sensitive data can be processed locally without being transmitted to the cloud. The ability to deploy compressed models in diverse contexts expands the reach of AI, bringing it into domains where bandwidth, hardware, or latency constraints would have made uncompressed models impractical. Compression, however, introduces compatibility challenges. Quantization and pruning often require hardware or software libraries that are optimized for low precision or sparse computations. Not all processors can handle 4-bit operations efficiently, and not all frameworks support sparse matrix multiplications at scale. This means organizations may need to adapt their infrastructure to fully benefit from compression. For example, a quantized model might run efficiently on NVIDIA GPUs with tensor cores, but not on older CPUs. These compatibility issues highlight that compression is not only about changing models, but also about aligning hardware and software ecosystems to support them. Overcoming these challenges requires investment in tooling, libraries, and hardware design that make compression benefits universally accessible rather than tied to niche setups. Combining methods is one way practitioners maximize compression benefits. Quantization, pruning, and distillation are not mutually exclusive. They can be layered for greater efficiency. For instance, a large model can be distilled into a smaller student model, pruned to remove redundant parameters, and then quantized to reduce memory usage further. Each method contributes differently. Distillation ensures the smaller model retains core knowledge, pruning simplifies the architecture, and quantization shrinks storage and computation. The synergy of these methods often produces models that are far more efficient than any single approach could achieve alone. This combination strategy reflects the reality that compression is not a one-size-fits-all solution, but a toolbox of complementary techniques. The art lies in blending them in ways that preserve performance while maximizing efficiency. Research into extreme compression pushes this blending even further. Some projects aim to reduce models to a tiny fraction of their original size while retaining as much accuracy as possible. Techniques like structured pruning combined with aggressive quantization and sophisticated distillation have produced student models that are only a tenth the size of their teachers, yet retain competitive performance. Extreme compression is particularly valuable for deployment on ultra-constrained devices such as IoT sensors or wearables. However, it remains an active research challenge, as aggressive reduction often risks catastrophic drops in accuracy or robustness. The pursuit of extreme compression reflects a broader vision: AI everywhere, running on devices of all scales, seamlessly embedded into daily life. Edge device applications illustrate the practical impact of compression most vividly. Consider a smart assistant embedded in a household appliance. Without compression, the assistant would require constant cloud connectivity, sending voice data to a remote server for processing. With a compressed model, much of the computation can happen locally, improving speed, privacy, and reliability. Similarly, IoT sensors in factories can run compressed models to detect anomalies in machinery in real time without waiting for cloud analysis. Even drones and robots benefit, as compressed models allow onboard decision-making with limited compute and battery resources. These examples demonstrate how compression brings AI from centralized servers into the physical world, enabling real-time, context-aware intelligence across diverse devices. Security implications accompany compression, and they are often underappreciated. Compressed models, by altering numerical precision or pruning parameters, may become more vulnerable to adversarial attacks that exploit these modifications. Quantized models, for example, may behave unpredictably under carefully crafted inputs that exploit rounding errors. Pruned models may lack redundancy, making them brittle under stress. Distilled models may lose robustness present in their larger teachers, leaving them open to subtle manipulations. While compression enhances efficiency, it can inadvertently reduce resilience. This means that compressed models require rigorous testing and adversarial evaluation before deployment in sensitive applications. Balancing efficiency with robustness is critical to ensuring that compression does not inadvertently introduce new vulnerabilities. Open-source contributions have accelerated the spread of compression techniques. Many researchers and practitioners share compressed versions of popular models, making them widely available for experimentation and deployment. Libraries and frameworks now provide tools for quantization, pruning, and distillation, lowering the barrier for entry. Open-source communities have created ecosystems where compressed models can be fine-tuned, benchmarked, and shared, fostering collaboration and rapid innovation. This openness has democratized AI further, ensuring that even small organizations or individual developers can access and adapt efficient models without needing frontier-scale resources. The culture of sharing compressed models mirrors broader trends in open science, emphasizing transparency, collaboration, and accessibility. Maintenance benefits are another hidden strength of compression. Smaller models are easier to update, retrain, and deploy as data evolves. When new information becomes available or a domain shifts, compressed models can be adjusted more quickly, since the resource demands of retraining are lower. This agility matters in fields like cybersecurity, where models must constantly adapt to new threats, or in healthcare, where emerging research requires rapid incorporation into diagnostic tools. Compressed models not only cost less to run, but also allow organizations to remain nimble, keeping systems up to date with minimal disruption. Maintenance ease transforms compression from a one-time efficiency gain into a long-term operational advantage. Cost reduction is perhaps the most obvious but also the most persuasive argument for compression in production environments. Running massive models at scale incurs significant infrastructure costs. High-end GPUs, cloud servers, energy bills, and bandwidth all add up quickly. Compressed models reduce these costs across the board. They consume less compute, require less storage, and can often run on cheaper hardware. For companies operating at scale, even modest percentage savings per inference multiply into millions of dollars over time. Cost reductions also open the door to new applications, as organizations can afford to experiment with deployments that would have been financially prohibitive with uncompressed models. Thus, compression aligns not only with technical efficiency, but also with business sustainability. Future research directions in compression point toward adaptive methods that respond dynamically to workload demands. Instead of applying a fixed compression strategy, adaptive compression would allow models to adjust precision, sparsity, or size based on the task at hand. For example, a chatbot might use higher precision when answering medical questions but lower precision for casual conversation. Adaptive compression could also adjust in real time to hardware constraints, scaling down on a smartphone while scaling up in a data center. This flexibility would make compression more intelligent and context-aware, ensuring that efficiency never comes at the expense of reliability where it matters most. Adaptive strategies represent the next frontier of making AI systems both powerful and practical across all environments. In conclusion, model compression encompasses three major methods: quantization, pruning, and distillation, that each address efficiency in different but complementary ways. Quantization reduces precision, pruning removes redundancy, and distillation transfers knowledge into smaller models. Together, they make AI smaller, faster, cheaper, and more deployable, extending its reach from cloud servers to edge devices. Compression is not without trade-offs, introducing challenges in accuracy, robustness, and compatibility, but its benefits far outweigh its limitations. As AI becomes increasingly embedded in daily life, compression ensures that advanced systems remain affordable, sustainable, and responsive to real-world constraints. These methods are not just technical optimizations, they are enablers of accessibility and scalability, ensuring that the power of AI is distributed more broadly across society. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.